Hello, welcome back to the Integrate Intelligently podcast. I'm your host, Jeff Brickler. Today, I'm again joined by my brother and CEO, founder of CAD Talk, Scott Brickler. And today, just kind of review, last episode, we introduced the concept of DFM, Design for Manufacturing, another acronym in the soup of acronyms that we have here in manufacturing. And DFM, Design for Manufacturing, we did a little primer, a little intro to high level, like what design for manufacturing is, what engineers are involved in manufacturing, what that looks like. So today we're going to dive a bit deeper into the process of DFM, really understand how's it implemented in companies, maybe even share some stories about how we've seen it with our customers. So Scott, it's great to see you again. Looking forward to this continued conversation on design for manufacturing.
I love this topic. I'm looking forward to it today.
So just as a recap, right? We talked about design for manufacturing last episode. We were talking about like what it is, why people would use it. We talked about different types of manufacturing, right? High mix, low volume, and low volume, high mix. So design, some people might think that design for manufacturing only applies to certain types of manufacturing companies, but I think we really know that that's not the case. So Scott, tell me a bit more about like, does DFM, Design for Manufacturing, does it really need to start early in the design process, or is it something that you do later? When would you do that?
That's a great question. I think that obviously it's like very kind of a uneventful response would be, it depends, right? You can think about, in my experience, getting involved early in the process tended to yield better results. Okay. And, but I've also seen an iterative approach work as well. I think that my experience has been that an iterative approach works better for higher volume, lower mix, and then a earlier process with lower volume, high mix. Okay. And more principles based approach at the high mix level. Okay. And let me explain that. Like when you're building like a car or like a cell phone or something that's on high volume, you have a little bit of an ability to kind of prototype and then refine, and you can do this iterative approach, and then you're kind of involving maybe manufacturing along the way, and you're making changes because you get a lot of swings at, swings at it, right? To kind of figure out how to refine it down and get it right. And you're doing a lot more prototyping and a lot more planning. So it's a little more of an iterative approach. And you're typically building something, you got to make it work first, right? And then kind of go from there. Whereas when you're doing lower volume, you tend to have people like the DFM part of it needs to be integrated because you don't get a lot of swings at bat, right? You have to kind of get it right the first time, and you tend to have more principles based approaches to it. Like, hey, try to use the same material, or let's try to keep all this parts on the laser, and things like that. Or let's standardize on certain hardware or material grades. And let's take a look at like how that, how that part is we can anticipate that part's going to be hard to mill because of this issue. And we can kind of have those. So I tend to see on the the lower volume stuff, the manufacturing engineering and the design engineering are working a little bit more closer together to get that optimization earlier in the process. So yeah, that's just my experience, but like, obviously there's a whole spectrum of how people do it. That's typically what I've seen.
So, I mean, one of the things I do is I speak to a lot, over the last 10 years, I think I usually tell people I've spoken to like 2,500 plus companies. I implemented 100 projects. I've spoken with a lot of engineers. I kind of joke sometimes. I can joke and poke fun a little bit at you and some of the folks that we work with. We love them to death, but engineers can be challenging people sometimes. And so you laugh because it's true, but we love them. I remember when I was teaching, I used to love those students who became engineers, very meticulous, very usually smart, and very challenging too. So I can imagine, probably because I've been on the end of this conversation, where engineers might push back and say, well, not my problem, right? You're slowing me down. I got designs to make. That's someone else's issue, right? Someone else's problem to figure out how to make this thing. My job is to make sure, fit, form, and function. Does it do what it needs? Because I have deadlines. I got things to do, right? So how would you, like, if you were going to consult with a design engineer, right? Whether that's like a younger person or a company, like how would you approach it?
Yeah, I think my standard kind of way I look at it is that you have to define the scope of the problem you're trying to solve, right? So if it doesn't do you any good, somebody would say that, well, that's not my issue. I got to make it work it work. I think usually you see that with a more junior person because it's hard. I mean, this is call it what it is. It's difficult to build. It's difficult to design things and make them work. So that's why I was saying you see a little bit more of an iterative approach, because like sometimes when you're building something, you don't know if it's going to necessarily work. I mean, so you're building it first and you're making it work. And then you have this iterative approach where you're doing a second draft or a third draft or a fourth draft or whatever it is, depending on how much time you have to then optimize for these different things like manufacturability, things like that. And then when you have less iterations to work with, you have to kind of almost model it in virtual reality, essentially in the CAD systems and stuff like that, to kind of guess that it's going to work and also try to get the optimizations out of it that you want. And engineers, the advice I would give them is that the scope of the problem is both. It isn't just making it work. It's also making it work and making it manufacturing in a way that we can actually come under budget and sell the thing for a profit. That's what the manufacturing problem is. So it doesn't do you any good. I mean, I could build a machine that does everything the customer wants for $1 million, but they're only willing to pay $200,000. It doesn't solve the problem. So the scope is actually different than you assume it is. So it's just kind of like, sorry, one of the requirements was it has to be cheap, be able to be made at a reasonable cost. And that's an optimization you have to deal with. It has to be manufacturable. You can design things in CAD that you can't actually make. That's actually possible. So those are all things that are it's part of the requirement. It's not really optional. Is it harder? Of course, but it's not really optional.
Right. So how would a design engineer go about thinking about like designing for manufacturing? Like who else would they involve in the organization? Like what kind of information would they need? How does that look?
Yeah. In larger organizations, you'll see there's actually a whole role for this called a manufacturing engineer who would kind of determine how you're going to go about making the parts with the capabilities of that company, right? Either internal or external, right? If they're going to outsource it or they're going to build it on the machine shop they have internally or whatever capabilities they have. So you have a manufacturing engineer who's familiar with that. If they don't have a manufacturing engineer, you could talk to the machinist or somebody who works in manufacturing or somebody in assembly, whatever the area is that you can get feedback of real-time feedback and experience that you're trying to share with somebody who's actually doing the work, like actually dealing with the thing that you designed. Those would be great ways to do. There's also tooling that will let you in the software itself that lets you kind of virtually assemble things or see how, tolerances work together. If you were to go with max tolerance on one part and then a min tolerance on the other and how they fit together and all that kind of stuff. There's all kinds of ways to simulate that with the tooling and the CAD systems and the different analysis tools that you can use that'll help you prove out some of those things. So there's lots of different capabilities of that, but like manufacturing engineer or talking to somebody who's actually doing the work is always good feedback.
Yeah. I also think about of course, talking to the people I also think about like, what data do you need, right? What data is important? I know as engineers, when I talk to engineers, for them, everything kind of lives and dies in the CAD or in the PLM, in the PDM, the system they use, right? Everything lives and dies in there. But the reality is, it's like, I've recently had some conversations, and I think this is kind of the origins of the product that we provide, CAD Talk DFM, where like it also gets into that some of the discussions we've had in the past about like data masters, right? In the sense of like, not all the manufacturing information, actually very little of it is in the CAD system, right? Definitely not in the CAD. Maybe if you had a larger package PLM that you have those kind of manufacturer bolt-ons, right? Team Center and Windchill have those, and some other PLMs will have these kind of manufacturing add-ons or bolt-ons where you can start to look at manufacturing. But unless you have those, either way, the ERP still has a lot of data around manufacturing, right? You got to put that data somewhere, right? You're going to either put it in ERP or you're going to put it in a PLM where you're going to have redundancies one way or another, right? If you're going to have manufacturing in PLM, you're going to have redundancies in ERP, right? So, but let's say you don't have that, right? How do you get that information, that manufacturing critical data to make a decision? Let's say I'm an engineer. I'm like, man, I bought in. I believe in DFM. But man, I gotta go over to SolidWorks. I gotta go out of SolidWorks, or I gotta go out of Inventor or Windchill, or I gotta go out of here and go over here and like look something up, right? Because I don't know. So like, how do I convince that guy to like do the extra work?
Yeah. Well, I think if you can codify, I mean, that's kind of what we do with our product. Not to shameless plug on our side, but like the idea is to surface those decision points data from like the ERP or other systems into the CAD system, so the engineer can see that to make decisions, right? So if you can surface the data closer to the decision point, Like when I'm making a decision about how I'm going to build this thing, then you give them better context to make those decisions. So like one of the things that we will do is like maybe show them a list of all the raw materials that are currently, in the system and what they cost, or availability of those raw materials, or maybe there's a rule in that we put in there. It says you got to pick from these three. So we're trying to drive consistencies, and we're trying to make it so you can do it correctly. I remember another example of this was like there's a tool I built when I was still working in manufacturing, which was we had engineers designing fabricated parts on a press brake. And then we had changed from using a coin press brake to an air bending press brake, which basically means that like whether or not when you say coin, you actually press the metal into the die directly, or you actually press it in and then leave an air gap underneath it. But then the bend radius in the forming or in the press brake was different. So they would actually, and then when the engineers were designing using the old machines bend radiuses and making parts that we couldn't make. So then we had to send them out. So he had to send them out to be made. And because it was somebody who had an old press brake. So we actually built a tool, kind of like a DFM tool type of thing, to automatically, when they pick the raw material from a select group that we always used, then it would actually set up their CAD system with the right bend radiuses, so they couldn't design things that couldn't work on our brake. So those are types of tools that you can use to surface up how you want them to design. That makes it like where they literally just, the easiest thing they can do is do it right. Which is kind of a design philosophy I have about a lot of things. I mean, it's a Scott Brickler original, but like, I don't think so. But it's just like if you want people to follow a process, you make that process the easiest process they can follow. And then they just kind of default to it. We default to human laziness, right? So like people will do whatever the easiest thing is, so make the right thing the easiest thing, and people will tend to do it.
Yeah. I think about it, evolution's optimized us to minimize the calorie expenditure, to minimize the effort of thinking, of the effort of anything, right? I want to do the easy, like it's primal, right? It's evolution. We can't hardly even force ourselves to do like hard, painful things, because it's everything in us is like, no, conserve energy, conserve thought, conserve. Don't try hard.
Yeah. There's actually a concept of like, called poka-yoke, I believe. It's like a Japanese term about creating these templates and these different ways of doing things to take a complex like setup or complex operation and make it like stupid simple, using like a kind of like a shadow board or something like that, but like a template. So therefore you actually can't get it wrong. Right. You just pull the thing out and it just like templatizes it. It's like stencils. Like stencils will be a form of that, right? Like a poka-yoke, right? So that's what they call that. And it just drives consistency in the most simplest way possible. Of course they're going to use that. It's just easier. It's just the easiest way to do it.
Yeah. It also limits the cognitive load, right? It goes back to that, the cognitive load of thinking. Like, I don't have to think about this, right? It's simple and fast and the easiest thing I can do.
Yeah. So to kind of get your original question, how do you make it so people do that? Is that you try to, and you want collaboration, because collaboration works really well, but collaboration is time consuming and engineers tend to avoid it. Like I used to be one, I used to do it. It's like talking to somebody is different mindset than designing something. It's a completely different mindset. So people, that's just the way it is. I mean, so you want it to be, typically when you're designing something or you're building something, you're in this kind of flow state of figuring things out and you're really moving, and you want to you want to kind of consult about the variables before you get into that state, right? So that's probably the best time to collaborate with your manufacturing engineers and others. And then you just want to go build it, right? Because that way you have all the constraints in your head. But then as you're building it, if you can surface up these things or create these tools in context that basically put those decisions on, speed dial, then you're more likely to kind of adhere to that, because the tools are kind of guiding you in that direction, even subconsciously. You don't even realize you're doing it.
Yeah. So this kind of gets into like design for manufacturing. There are principles, but those principles are going to be applied. You apply the principles the same across every manufacturing company, but what that looks like at every manufacturing company is going to look a little different, because like what they have on site or what they have, like you said, the type of material they use may be different, just because like, to this one company, because like the mill was like down the road. It said, we use this material. Or like, well, why do you use that? Well, we don't really need to use that. We can use something else, but like it's down there. So we can get it faster. We can get it same day. Like all these things that they're able to do. my point to this was like DFM, when you design for manufacturing, it's not going to be like, I can't give you like always do this to every manufacturing company, right? Because like always design this way or always use, some kind of pre-built process that's going to work for every manufacturing company. I think it's more like principles, right? We have certain principles, that things that we know that work, and make a tool that, or whatever the tools you use, right, to make it easier to make those decisions, to do those things, to get that information. Whether that's going to be like the sustainability, right? For design with sustainability in mind, like, hey, which of these things is has the, so some ERPs have this, has the biggest like CO2, like the biggest footprint, right? Some ERPs are tracking this, you might say. These are the kinds of things that you can decide on, but it might be different depending on the organization, on all of that, right? So there's no one blueprint. I can just say, here, everybody's going to do it like this.
Right. Yeah. But the principle of how it's once again, like we talked about in the first episode, is what you're optimizing for. So if you're, and then you have to decide as a company what you're optimizing for, and then set up the tooling and the decisions and the structures around setting up for that, the best optimization of those things that you want to optimize for.
So, kind of last thing, Scott, we're going to, before we let you go and in this episode and wrap it up, what are two examples of like good practice for design for manufacturing? If we're going to give somebody a template, what would we say as the template?
Yeah, I think it's hard, like, because it depends on, if they're high mix, they're high mix, low volume, and that, those are all kinds of variables that you'd have to know for sure. But I think that the idea that if I had to do an overarching, would a good template be like, you have to figure out how you're going to make the thing that you have with your capabilities, right? And if you're outsourcing, you pretty much have every capability in the world, but you're also going to think about, if I'm low volume, high mix, then I probably want to optimize on lead time. So sending it out may not be the best thing. If I have the capability in house to do it, and get the same essentially functional, form, fit, and function work the same, then do that. Collaborate. Typically talk to the people who actually talk to people who are putting it together, who are building the thing, talk to customers and how they're working with it, and then take in all that feedback to generate more, especially if you have high mix, to generate general principles around how you design. Because you may not have another pass at the existing design, but you at least have principles that you can apply overarching principles to everything else. If you have high volume, then you have a lot more variability. You can do a lot more iterations, because you're like, last year we did this and that part kind of stunk. We didn't like that. So let's do that a little better. Right. And you have a little bit more volume. And then that collaboration from the customers as well as the people will tend to be, you can do a much more iterative approach and really refine it more and more.
So you're getting feedback on because there's a lot of volume. You get a lot of feedback on yes. You get a lot of more better data of like, okay, this, like when we used to work on cars, right? Certain cars, probably less so now, but I think it still happens. Like, this part always went bad on these types of models, right? I remember our dad used to know all of that. Like, I'm sure lots of Midwest dads would be like, know that, like, oh man, on those Ford, when we were kids, those Pintos, they always the clutch went bad. Always the clutch, right?
Yeah.
Or exactly. Whatever. So, yeah, that's good. I'll leave it with this. The one thing I thought of, maybe more of a primitive mind myself, not being an engineer, but I was thinking the simplest kind of thing you could give for design for manufacturing is like a template item, a template routing, right? Like,
sure,
hey,
yeah.
That's, just this like really simple thing. Like, hey, do you have kind of categories of parts that look like or can be made out of, like, hey, parts of this type always get made out of this material and have this routing and like this run times, like this stuff, right? And now you say, well, if I make this part, I know if I make this part, but in this template, right, in this kind of box, I know I'm going to get, right? I have that consistency.
Yeah, and you can get an idea of a rough cost and you get some feedback on that because you've templatized how you make things around certain families of parts. Yeah. That would be very useful.
Yeah. So just my basic mind working there. Well, Scott, this was good. So a good introduction to DFM last episode, and a little bit deeper in this episode about the practical use cases designed for manufacturing. Also, how to get engineers on board. General principles. around like making it easy, right? We talked about like making it easy for people. So I think those are good principles just regardless, manufacturing or otherwise. So I think, next episode, just a preview, Scott, we're going to talk a little bit about like what happens when DFM, there isn't design for manufacturing in a company, right? What happens when, you do that, but it made an error, right? They're mistakes. So how do you deal with those? So, Scott, it's been another great conversation. I appreciate you for joining this week. Look forward to the next episode, episode 18 in our series of DFM. So part 3 is coming up next week.